Hey guys, welcome back to my YouTube channel. So, the most weighted topic that we are going to start today. So, that is on PN junction. So, see, the last lectures, the sequence of lecture, I think some 40 plus lectures, we have shown only on the separate things, like how the individual N type and how the individual P type will react. But now, we are going to see when we combine both the things. I think already in one of the lecture we saw about some depletion region, those things. So that is quite small introduction. But here we'll be going to study detailedly on how the things will be changing. So I have taken a PN junction. So this is here P will be donor acceptor atom and N will be a donor atom. So Na and D. So we know how to represent, that is with the power script of holes. So which will be uniformly doped. So here we are not conferring non-uniformly doped things. So everything here is uniformly doped. Above is represented with holes. So in N type, above is represented with electrons. So donor atom. Okay, this is how. So though it is on P type, there will be majority and minority charge carriers will be there. So let's draw the majority and minority charge carrier over both the region. So here is the consideration. This is the profile of free carrier concentration. That this region that we can call this as a, this is PP, means the majority charge carrier in P type. Though majority charge carrier will be P, so PP. So this is minority charge carrier N in P region. So this is how the representation that we follow, that you guys already know. The below subscript is used to indicate the region. So here you can say that is NN and PN. Okay. So here we are considering the same term. So both side uniformly doped. So both things are same. At x is equal to 0, which is eventually coming here, and that will be changing to high profile. So that is completely the same. So this is what the profile that here. So here nothing is happening. So no diffusion or no charge carrier, anything happening. So this is a carrier concentration at neutral equilibrium. Carrier concentration at equilibrium. Okay. So I hope it is understood for you guys. So let's take an PN junction diode with some inbuilt electric field which is coming into picture. So let's take a region of built-in region here like this. Okay. So here what will happen, because of some inbuilt electric field which is acting from this region to this region, some inbuilt electric field that is acting. Okay, how the inbuilt electric field will happen is because of the diffusion of charge carriers. So I will know how to say it. So here there is the same thing. So here there is no thing. But here what's happening? How this depletion region is formed is that the holes from here are diffusing to this side and electrons from here are diffusing to this side. So this is causing some kind of depletion region and charge neutrality condition is lost here. So that is for the condition that we are seeing here. So if this is the case, then the electrons will also be lost here, right? So then there will be only donor atoms. So here there will be electron, but in the depletion region all the electrons and holes are lost. So this is the region where we call as depletion region. We'll be mentioning as WD. Okay. So I hope it is understood. So because of this only this electric field is created, which is inbuilt electric field from positive to negative. It's okay. So when this is happening, how the profiles will be changing, that I am going to show you now. So let's take this. I'm taking the exact region of the depletion region things. Okay. So let me erase it. So here, before this is happening, that the carrier concentration will be same as it is. So like the previous cases, the carrier concentration that will be same. So here you see, here you are seeing, right? So it will be similar to that. First let me represent completely and then let me erase it. So up to this, before this region, the carrier concentration will be same. There will be no changes. Okay. I hope you guys are able to get it right. So once this is coming in the depletion region, we know that the dp by dx will be decreasing here once in this region. So in this region, we know dn by dx is decreasing here, dn by dx. because that is coming here. Here there is more free charge carrier is there, but here it is coming decreasing. Okay, then what will happen? Eventually it will be falling like this, and it will be changed here. Here we said, right, so this is the p-type charge carrier, this is p-type charge carrier, here it is n-type charge carrier, n-type charge carrier. Similar to that, it will eventually come here and fall to minority charge carrier here. And this, the minority charge carrier in a n-p type will eventually increase here and will become a majority charge carrier here. So this is how the representation that we will be following here. I hope you guys able to get it right. So even if you know, let me get it in a short way. So here you know the holes is the majority charge carrier, but here the electrons are the majority charge carriers. So where in the p-type region the majority charge carriers eventually fall and becomes a minority charge carrier in n-type. Here the minority charge carrier of electrons will be eventually increasing and become majority charge carrier in a n-type. So that only we are making here. So I hope it is now understood for you guys. So this point we will call as a xn, and this point we will be calling as minus xp. Okay, so this is to mention p region, this is to mention n region, because as we taken reference x is equal to 0 here, right? So that's why. So further, if the depletion region increases, this charge carrier depletion will be start increasing from that side. So now we can clearly say the wd, which will be equal to xn plus xp, or modulus of xp. Okay, so this is one of the very important term. So I hope in the PN junction how the charge carriers and how the inbuilt electric field is coming, that you guys know. Here you see from here the holes will be diffusing to this region. From here electrons will be diffusing to this region, so that some depletion region will be formed. So this depletion region is very much important. So this is at an equilibrium. So no external supply is produced. So when we supply external based upon the forward bias or reverse bias, the increasing depletion region or decreasing depletion region will happen. So that we decrease that we discuss in the upcoming lectures. So for now, what you have to understand is the how the both the junctions are coming into interaction. Because of the interaction, how the charge carrier diagram is getting displaced like this. Here also same thing. Here you see the majority charge carrier here. It will be eventually coming here and will be dropped abruptly from abruptly here to minority charge carrier. But here what's happening, which is slowly dipping here. So that's what I'm mentioning here, which is slowly increasing here, slowly dipping here. Here you see it's abruptly coming down and it's abruptly going down. If you need, I will be representing in different color. So this will come and it will abruptly going to minority charge carrier in another region. That is normal as it is. But here if you see, which is coming and slowly decreasing to other region. Okay, so this is what the biggest difference between the normal thing and with the depletion region. So the WD, which is one of the important term, depletion with the, so we can discuss that clearly in the next upcoming lecture. More things that we can discuss in the things. Okay, so let's take an example like how the dipping and diffusions will be taking place here. So the direction of flow of particles is that the holes will be diffusing to this region and electrons will be diffusing to this region. So because of this internal built-in electric field, some kind of other electrons and holes will also be diffusing in the opposite region, so that the net current flow will be zero. That we guys already discussed, right? So the thing is that at equilibrium without external supply, everything will be equal to zero. So at equilibrium, what will happen is the IP drift plus IP diffusion, not J, IP drift plus IP diffusion. Both will be in the opposite direction, so that will be equal to 0. Similarly, IN drift plus IN diffusion will be equal to 0. So IN diffusion. Let me clear it. The diffusion is happening because of charge carrier variation. Diffusion is happening because of P type and N type charge variation. So the charge carrier will flow from higher concentration to lower concentration. So charge variations. Charge carrier variation. The diffusion, sorry, drift is because of the inbuilt electric field. Because of inbuilt electric field that is developed. So because of that is some drift movement will be take place. So movement of charge carriers. Movement of charge carriers. But both will be in opposite direction, so that the total current I net will be equal to 0. So this we already discussed in the semiconductor discussion on itself. So without external supply, nothing will be there. So everything will be at equal to 0. So the thing that we saw, right? So in the previous diagram, this is just an approximate diagram. But in most of the cases, we will be using the exact diagrams. So let me go through how the exact charge carrier diagram can be represented. So let's take a case, the same case that we wrote there, right? So the same diagram. Okay. So this is the depletion region. Let's take this is a XP minus XP, and this is positive XN. So let me make it a dotted line. You guys will understand the PN junction. The very best level I haven't here before. So stay tuned, guys. So let's draw the charge carrier diagram here. So the charge carrier will be, as we know, it will be constant from here to here. So there will be no change in the charge carrier. It will be same here to here, and it will be same here. So this is, I am representing P type in the red color region. Okay. So if we draw the electron concentration here, that will be same here, and that will be same here. The magnetic charge carrier will be coming majority charge carrier here. But in the in between region, it will be drifting towards like this way. It will decrease. The profile will decrease, and it will eventually reach this one. In this one, the magnetic charge carrier in the P type will eventually increase and become majority charge carrier in the N type. Okay, so this is how the quite difference. So this is NN and this is PN. This is PP and this is NP. Okay, so this is X is equal to 0. This is XN and this is XP or minus XN modulus anything. So in another one diagram, the approximation diagram where the charge carriers, only the change in carriers, the charge carrier density, the charge density can be represented somewhat quite different here. How they will represent the charge carrier is that the charge carrier change only they will mention here. So let me take a blue color here. So charge carrier will be eventually falling on the same line because there is no net change in the charge carrier. Here if you see in the P type, eventually in the depletion region, only the holes will be diffusing to another region. So the thing is that only acceptor atoms will be present here. So that we are using this one. Then in the opposite end, there is only the donor atoms will be presented here, and other here there will be nothing. No donor atoms will be there with some electrons. So here it is positively represented. So this kind of depletion region in this one in the below diagram charge density, we are representing only the charge carrier which is lost to the electrons, not the entire charge carrier, only charge density in the depletion region that we are mentioned here. So this one can approximately even written. This is some, you can see this is not approximate. This is not a perfect, even not a square or anything. So this cannot be used for any mathematical calculation. So the approximate calculation, how we can modify is that the simple square log model, like similar to the square log model, we will be representing the depletion region things in a square way, like to find out the areas of those things. So this approximation model, not a perfect model. In the real scenario, it will be like this only, but the charge carrier changes will be quite lower, or the variation or this approximation model will result in a small negligible error. So the inventions and scientists are using these models. We know, right? So everything in this world are approximated, right? So here that will be equal to traces. It will traces the boundary. It will traces the boundary here. Then eventually it will decrease here, and it will form a square kind of things. So that is what I am saying as a square log model. I hope you guys getting right. So this is negative. So this is only acceptor atom, and here only donor atom. So this is one kind of approximation that we use for all the mathematical related studies. So I will be letting you know why we took this and how we will be proceeding further next lectures. So for now you can know that is depletion approximation. So this is depletion approximation. So this is depletion approximation, because in this way, if we need to find out the area, then integration will be very difficult here. But here the integration will be just a area, will be xn divided plus this height charge carrier. So this will be very easy for us to analyze. So that's why we are taking this approximation model for our all the analysis in the going forward PN junction diode. So this is one of the very important thing. So I hope you guys getting some idea, right? So how the charge carrier will variation. Nothing we have seen. So these things we already discussed in the semiconductor physics lecture itself. So that's why I have said the semiconductor physics basics is very much needed in order to understand BJT, PN junction, MOSFET, everything. So I hope now you guys able to get it in a very easy manner. So stay tuned, guys. This will make you to get land in a very good understanding of the semiconductor physics. Okay, thank you, guys. Thank you. Please stay tuned, like, share, and subscribe channel.